Okay, so now we're going to do some example problems on significant figures. And this stuff, again, should be pretty easy. I think hopefully you guys remember how to do this. So the first one here, what's the difference between 4.0 grams and 4.00 grams? That one I probably don't really need to write the answer to, but the difference there, maybe we could talk about the number of sig figs. So 4.0 grams is going to have 2 sig figs. 4.00 grams is 3 sig figs. Okay, but the real difference, what they're asking for there is one is measured more precisely than the other, and the 4.00 gram one is going to be more precise. Okay, that means that we used a better instrument to measure that with. We were able to measure it to a greater degree of accuracy. Okay. All right, next one. How many significant figures are in each of the following numbers? Assume that each number is a measured quantity. Okay, so A here, 4.003. That one has 4 sig figs. Okay. And then B here, 6.02 times 10 to the 23rd. We talked about this a little bit last year. You may not remember this as well. Sorry, this 6.023 is the way that it's written there. 6.02, let me try that again. 6.023 times 10 to the 23rd. Okay, and the only part of that number that matters as far as significant figures is the first part. Okay, there's 4 sig figs there, and so that's going to be 4. Now, going back to this, there are 2 zeros in this number, okay, but they're both in between significant numbers, so they count. Okay, and then the same thing with this 0 down here. It counts because it's between significant numbers. Now, on C, 5,000, there is no decimal point after that number, so these are zeros after a number without a decimal point. They're not going to be significant, okay? So there's only one significant figure there in that last number, okay? Now if I put a decimal there, there would be 4. Okay, next one, the width, length, and let's see what's going on here. The width, length, sorry, button's not working for some reason. Okay, so the width, length, and height of a small box, 15.5 centimeters. It gives you the dimensions there. Okay, so we got to remember that volume equals length times width times height. So we're taking 15.5 centimeters times 25.3 centimeters times 5.4 centimeters. Okay. When we multiply all those together, we've got to figure out how many sig figs we should report that number to. When you put that number into your calculator, you should get 2,117.61, okay? But we're doing a multiplication here, so what you have to remember is the number with the least number of sig figs. That's the one that we round the answer to, okay? There are only 2 significant figures in this number, and that's the one with the least number of sig figs. So we're going to round our answer to 2 sig figs. All right. Now, how do we round 2117.61 to 2 significant figures? What you don't want to do here, and this is what people struggled with last year, you don't want to round that to 20. Okay, that's not the same number, right? You want it to stay basically the same number. Okay, so you've got 2,117.61. We're going to round to this place right here. So we're going to make these 2 numbers into zeros. Okay, so we're going to round this to 2,100. And again, don't forget your units on these, centimeters cubed. And that's going to be our answer on that one. Okay. So again, watch when you're rounding. Make sure that you don't change the number of places in the number. Okay, this number right here, this 2, is in the thousands place, and the 1 is in the hundreds place. When you round the number, you still want the 2 to be in the thousands place and the 1 to be in the hundreds place. Okay. All right, next one. Gas at 25 degrees Celsius fills a container previously determined to have a volume. Gives the volume. Container plus the gas are weighed and found to have a mass of 836.7.6 grams. The container, when emptied of all gas, has a mass of 836.2 grams. What's the density of the gas? Okay, so what we want to figure out here is, this is essentially a density problem, but it's a difficult one. So the volume of the container is 1.05 times 10 to the third, and it says that the gas completely fills the container. So we know that's our volume, 1.05 times 10 to the third centimeters cubed. Okay? Container plus the gas are weighed and found to have a mass of 837.6 grams. And then it gives you the mass of the container without the gas in it. Okay? So our mass here, we're going to have to take the 837.6 grams. That's the total mass minus the 836.2 grams. Okay, that's going to give us our mass. Now, there's two different types of, this is really a significant figure question, even though it's a density question as well, because there's two types of things going on here. When we plug this into D equals M over V, we're going to be doing a division, okay? But before we do that, we have to do a subtraction, okay? So you've got to think about both of your sets of rules here. So 837.6 minus 836.2 gives us 1.4, okay? Now, you might be thinking on this one, oh, well, that's only 2 sig figs. Both of my numbers here have 4 sig figs. Well, when you subtract, remember, what you have to do is you have to line up the places here. So we've got 837.6 minus 836.2, okay? Both of these are significant to the 10ths place only, okay? Which means we're going to round our answer to the 10th place, and it's already rounded that way. So we're only going to have 2 significant figures in our answer for our mass, okay? So when we plug that in, 1.4 grams divided by 1.05 times 10 to the third centimeters cubed. And now we're doing a division, so we find the one with the lowest number of sig figs, which is going to be our top one here, the 1.4. That only has 2 sig figs, so we're going to round our answer to only 2 sig figs. Our density here is a low number. It's 0.0013, okay? And that's going to be the right number of sig figs because these zeros are before a number they don't count, okay? Now, there's another way you could report this number. If you wanted to do it in scientific notation, you could write down 1.3 times 10 to the negative third grams per centimeter cubed, and that would be fine too, okay? Either way works. Alright, so let's move on to accuracy versus precision here, real quick. Okay, so we just finished talking about significant figures. Get this out of the way here. Accuracy versus precision. Accuracy is how close the measurement is to the value. In other words, how correct you are, okay? If you throw darts at a dartboard, you get them all in the bullseye. That's good accuracy and good precision, okay? Precision is how close the measurements are to each other. So in this second example here, this is good precision, bad accuracy. You're throwing in the same spot every time, okay? And that could be a result of systematic errors. If you're constantly throwing a baseball off to the right, then you probably need to work on your mechanics of your throw, okay? If you're measuring incorrectly in the same place each time, then you may have something wrong with the equipment you're using, or you may be measuring it in the wrong way, that sort of thing. Now, if you have poor accuracy and poor precision, that's probably just the error of the person making the measurement, okay? All right, dimensional analysis. What do virtually all chemistry problems have in common? I'll bet you can't guess. Dimensional analysis. That just means we're taking one unit and we're converting it into another. That's usually what we're doing with dimensional analysis, okay? So convert centimeters to feet. Here's an example. 1 centimeter equals how many feet, okay? Now here's the things that we know. 2.54 centimeters equals 1 inch, and 12 inches equals 1 foot. So we did this last year, and I had you guys set these up in a very specific way. If you're coming from a different class, you might have learned this a little bit differently, but I think this way works pretty well. When you're doing your conversion, all you're going to do, I'm sorry, we're starting with 1 centimeter. We want to know how many feet 1 centimeter equals. So we're starting with 1 centimeter, okay? Then we're going to do a conversion here. And because we're starting with centimeters, we're going to put that unit on the bottom, okay? And then whatever unit we're trying to get to is going to go on top. Now, what we would want to put here is we'd want to put feet. Problem is, we don't have a conversion directly from centimeters to feet, okay? So we can't do that. We've got to go to inches first, because that's the conversion that we have here. So we're going to go from centimeters to inches, okay? There are 2.54 centimeters in every 1 inch, okay? And then we're going to cross these out. And you can make some sort of noise when you do that if you want to. Some of my students last year liked to do that. So now we have inches. That's our unit, okay? So that's the one that's going to go on the bottom. Again, we got to think about where we're trying to get here. We're trying to get to feet. Okay, and we know that there are 12 inches in 1 foot. Okay, so now our inches cancel out, and now our units are in feet, and you can stop. And basically what this tells you to do, this is just a setup that tells you whether to multiply or divide to make these conversions. So we're going to start with the number 1. When you punch this in your calculator, you're going to divide by 2.54 because it's on the bottom of the fraction. Okay. And then you're also going to divide by 12 because it's on the bottom of the fraction. If your number is on the top of the fraction, then you would multiply. Okay? Once you do that, take the 1 divided by 2.54, then divide it by 12. 0.0328 is the number that you get. Now, if you're watching sig figs here, I gave you, excuse me, gave you 1 sig fig in your beginning unit. Okay? So your answer needs to have just 1. So we're going to round this to 0.03 feet. Okay, and that's your answer there. Okay, next. Oops, sorry, you're written. Well, that's better anyway. Okay, so the questions you need to ask yourself here: what do I need on top? What do I need on the bottom? What do I know? How do I get there? And that's the process I just showed you. Okay, you're always going to be given the conversion factors you need. I can't think of any off the top of my head that you really have to have memorized for the AP exam. I guess the ones that you might need to know are like centimeter, millimeter, deci, those type of metric prefixes. You would probably need to have those memorized, but any other conversions that you need should be given to you. Okay? So, some examples here, and I've got a lot of sample problems on here, and I'm probably going to let you do some of these on your own. But we'll go over a couple of these together. So, first off here, speed of light is 2.998 times 10 to the 10th centimeters per second. What is it in kilometers per hour? Okay, now, this is a tough one because you've got centimeters, and those are not lined up. Tell you what, I'm going to do this on a separate page here, and I'll just walk you through how this works. I think that'll be better anyway, so you can see the process. Okay, so the hard thing about this one is you're actually starting with 2 units. So you've got 2.998 times 10 to the 10th centimeters per 1 second. Okay, that's the way that I kind of like to write this because it shows me where my units are. Centimeters per second is really the same thing as what I just wrote. Okay, we want to know what it is in kilometers per hour. Okay. So we're going to have to convert seconds into hours. We're going to have to convert centimeters into kilometers. So let's start with centimeters here. You may be able to do this conversion. If you're not, probably the easiest way to do it is just go to the base unit first. Okay. And according to your chart that you have earlier on these notes, there's 100 centimeters in 1 meter. And then we can go from meters to kilometers. Okay. And there are 1,000 meters in 1 kilometer. Okay? Now, that takes care of the kilometer part of things. Now we've got to go from seconds to hours. Okay? So here's the tricky part. I'm just going to continue this thing. Okay, so you got to just think of this as all continuing on one line. Because we had seconds on the bottom at the beginning, in order to cancel out that unit, we have to put seconds on the top of our fraction here. Okay, so seconds, again, you might know how many seconds are in an hour, but if you don't, just go to minutes. Everybody knows there's 60 seconds in a minute, I hope. Okay, that cancels out seconds, and then we'll go from minutes to hours. Okay, 60 minutes in an hour. If you knew the 3600, which a lot of you I'm sure did, then that's fine. You can use that conversion also. All right, so then what you're going to do when you punch this into your calculator, 2.998 times 10 to the 10th divided by 100 divided by 1,000 times 60 times 60. If you do all that together. Now, if you want to break that up into two separate parts, you can also do it that way. But that's the way it works best in my head. So when you do all this, the answer I'm getting here is 1.0 sig figs right here. First number on these conversions is usually the one you want to look at for your sig figs. 1.079. That's the right number, sig figs, yep. Times 10 to the, let's see, 9th kilometers per hour. That's a K. Alright, so that's how that works. That's a pretty good example of how you do the dimensional analysis. Alright? They rounded that a little bit differently than I did. Or else my number's a little bit different for some reason. It's close. Alright. So next here, we've got another example. And this is one that they might expect you to do as well. Move this out of the way. So you've got this vehicle assembly building at the Kennedy Space Center, and it tells you the volume. What is that in liters? Okay, so you got to remember some conversions here. Okay, and the conversions you have to remember. We'll do this one too because this one involves a cubic conversion, and those are a little bit tougher. Alright, so we've got 3,666,500 meters, big number there, cubic meters. And we need to get into liters. Now, the thing that we know from earlier in the notes, we know that 1 cubic decimeter equals 1 liter, right? So it might be a good idea to go from meters to decimeters, and that could get us to liters. It's probably the easiest way to do that. The problem here is we can't just put meters on the bottom, decimeters on the top, because this is cubic meters, not just meters. Okay, so here's the trick on this one. There are 10 decimeters in 1 meter. Okay? We know that conversion, and then we just have to cube the whole thing. Okay? That will get us to cubic decimeters. Alright, and then once we've done that, and this step you don't necessarily need to write out, but we know that in 1 cubic decimeter, that is 1 liter, okay? Because that was the conversion that we learned earlier when we were talking about volume. So once we work all that out, then we should be able to figure out the answer to this problem and then work out how many sig figs we need to put in this number. I should say this about the AP exam, and I'll probably say this in class too. On the AP exam, as long as you are within 1 significant figure of what you're supposed to be, they will not count off. If you are 2 or more sig figs off, if you report your answer to the incorrect number of sig figs by 1 or 2 decimal places, then they'll start counting off on that. So you got to be a little bit careful there. So what I'm getting here, I probably should have been able to do this one in my head, 3.6665, that's a big decimal, times 10 to the 9th liters. Okay, So that's my answer for that one. The rest of these give you the conversions, and I think you should be good converting the rest of these. They're very similar, okay? So you can try the rest of these on your own, see how you do, but that's dimensional analysis and that's significant figures. Two of the things I know you guys love best about chemistry, but we have to do that stuff before we can get into any of the harder calculations. So that's that. See you next.